Welcome to This Explainer. You know, when we think about robots today, we usually get completely caught up in their brains. The advanced artificial intelligence, the millions of lines of complex code, the lightning-fast microprocessors. But honestly, all of that incredible processing power means absolutely nothing if the robot can't actually interact with the physical world around it. So today, we're going to pull back the curtain and dissect the mechanical muscles that breathe physical life into modern robotics.
Here's a quick look at our roadmap for today. We'll be starting off with the muscles of machines, checking out the big three actuators, and then doing a showdown between electric and pneumatic power. After that, we'll look at engineering the perfect muscle, see these in the real world, and wrap up with the very cool future of actuation. Let's get right into it.
Section 1. The muscles of machines.
Think about it for a second. A static robot sitting completely still is really just a tremendously expensive metal sculpture, right? So what actually bridges the gap between a line of code and a physical action? Well, just as biological systems rely on neural signals to trigger a muscle fiber contraction, industrial automation needs a kinetic equivalent to execute digital commands and move around in the real world.
Enter the actuator. This little component is absolutely crucial. It is the literal bridge between a robot's digital brain and the physical world. Basically, they receive a signal from a control system and they execute the corresponding physical movement by converting stored energy into mechanical motion. Whether that's rotating a joint a tiny fraction of a millimeter, moving a heavy conveyor belt exactly 3 inches, or gently grasping a fragile object so it doesn't get crushed, the actuator is the unsung hero doing the literal heavy lifting behind the scenes.
Moving right along to Section 2. The big three actuators.
Just like biological organisms use different types of muscle fibers depending on whether they need endurance or explosive power, robotics relies on 3 primary flavors of force. Engineers have to choose between electric, hydraulic, and pneumatic power depending entirely on the job at hand. Need pure finesse? Well, electric actuators convert electrical energy into mechanical motion using motors, and they offer incredible precision for things like delicate surgical robots. Need raw, brute strength? Hydraulic actuators are your go-to. They rely on Pascal's law, using pressurized fluid, which is usually oil, to create the immense force needed to lift massive, heavy loads. But what if you need rapid reflexes? That's where pneumatic actuators come in. They use compressed air to expand and push against a piston, giving you the high-speed, super reliable motion that you'll find everywhere in high-volume packaging and sorting operations.
Next up, Section 3, the electric versus pneumatic showdown.
Let's actually put the 2 most common factory muscles head-to-head to see how they stack up in a classic engineering face-off. When you look at them side by side, it's pretty clear that electric actuators are the ultimate choice when exact precision is the goal. Because they use programmable controls and advanced feedback systems, they can stop at any exact point during their operation. That makes them absolutely perfect for clean rooms and high-tech manufacturing. Plus, they boast really great energy efficiency since they don't need oil or air. But, on the other hand, pneumatic actuators offer a lightning-fast response that electric motors often really struggle to match in rapid repetitive tasks. And here's a massive advantage. Because they don't rely on electricity at the actual point of action, they are completely spark-free and explosion-proof. So if you're setting up a chemical plant or an oil refinery, pneumatic actuators are without a doubt your safest and most reliable bet.
All right, Section 4, engineering the perfect muscle.
Let's head into the design lab for a second. Every single time a robotic system is designed, engineers are constantly juggling this whole list of critical metrics to ensure the muscle perfectly matches the job without wasting a drop of energy. For example, if you need a robot to hoist a heavy engine block, you are going to heavily prioritize force and torque. But if you're designing a robotic arm for a fast-paced assembly line, speed and response time take the front seat. And on top of all that, you always have to consider physical constraints. How much does this actuator weigh? Can it dissipate heat effectively? Engineers have to meticulously optimize every single one of these variables because honestly, an overheated, inefficient actuator can stall an entire multi-million-dollar assembly line.
And that brings us to the ultimate make versus buy dilemma. Designing an actuator for purpose, or DAP, means you are custom building it in-house. You control every bearing, every motor, and every seal. That is absolutely mandatory for something like microscopic medical devices where no off-the-shelf part is ever going to fit. But procuring an actuator for purpose, or PAP, gives you an off-the-shelf, plug-and-play solution that usually comes right out of the box with its own software drivers. It saves massive amounts of internal engineering workload and gets your product to market drastically faster, even if it means you have to make a slight design compromise here and there.
To give you an idea of just how insanely precise this engineering has become today, take a look at this number. Modern planetary gearboxes for industrial robots can now achieve a torsional backlash of less than or equal to 0.1 angular minute. Just let that level of accuracy sink in for a second. Normally, when a robotic arm swings around at high speed and suddenly stops, any mechanical play or looseness in the gears causes a jolt. But by using specially designed conical toothing that presses the gears perfectly into one another, engineers have essentially eliminated this backlash. This is what allows robots to maintain microscopic precision over their entire operational lifespan.
Let's move on to Section 5, Real-World Robotic Muscles.
It is genuinely amazing to look back at how robotic muscles have evolved over time. We've moved from massive, dangerous machines that literally had to be locked in cages to highly sensitive, smart cobots that can safely hand-guide and sense exactly how much force they're applying. Decades ago, if a human accidentally got in the way of a robotic arm, the arm wouldn't know to stop. Today, actuators are incredibly smart. Engineers are using revolutionary technologies like applying a micro-thin, strain-sensitive metal coating directly to the drive shafts, which effectively turns the physical component itself into a torque sensor. This means a collaborative robot instantly senses even the slightest resistance and stops before it can hurt a human worker.
If you walk onto a modern automotive assembly line, you're looking at a beautifully cohesive ecosystem where brute hydraulic force, rapid pneumatic speed, and exact electric precision are all seamlessly collaborating. It's like a symphony of actuators. First, you have the hydraulics doing the extreme heavy lifting, safely moving literal tons of metal around the factory. Then step 2, you have pneumatic actuators acting as the fast-twitch muscles, rapidly snapping and feeding parts into place along the conveyor belts. And finally, step 3, the electric actuators take over for the fine motor skills, hyper-precisely guiding welding torches and spray paint nozzles with millimeter accuracy.
Finally, we arrive at Section 6, the future of actuation.
So where is all this robotic engineering heading next? Well, look at this number. As we push toward advanced humanoid robots, engineers are desperately trying to cut the weight of joint actuators by a massive 40 to 50% just to make them viable. Think about a humanoid robot for a second. Every single ounce of weight in its arm requires more power to lift. More power requires a bigger battery. A bigger battery adds more weight. It's a total vicious cycle. To make untethered, human-like robots a reality in our daily lives, the actuators inside their joints have to become radically lighter without losing an ounce of their strength. To actually solve some of those major challenges, the industry is starting to shift away from rigid metal and into the era of soft robotics. Here, compliant materials can safely handle fragile objects and adapt to totally unpredictable environments. A great example is pneumatic artificial muscles, or PAMs. These literally bulge and contract just like your own biceps do when you lift a weight. And because they're made of flexible materials, they naturally conform to the shape of an object. This is an absolute game changer for tasks like robotic fruit picking or advanced prosthetics, where having a gentle, adaptable touch is just completely mandatory.
And then there's the truly sci-fi stuff. Smart materials. We're seeing the rise of materials that literally change their physical shape in response to stimuli, which allows for microscopic, totally silent, and highly efficient robotic movement. Imagine an actuator with no moving gears whatsoever. Shape memory alloys can be deformed and then instantly returned to their exact original shape the moment they're heated. Piezoelectric materials deform instantly when exposed to an electric field, granting nanometer-level precision. This completely removes the need for complex mechanical gears and paves the way for robots that operate silently and at a microscopic scale, potentially even navigating inside the human bloodstream for targeted medicine one day.
So as you think about this incredible journey from clunky gears and massive hydraulic pumps to these soft, bio-inspired smart actuators, it really leaves us wondering just how biological the robots of tomorrow will truly feel. The lines between mechanical engineering and actual biological mimicry are blurring incredibly fast. We've seen how actuators are the true muscles bringing machines to life, and as they get smarter, lighter, and softer, the possibilities out there are genuinely limitless. Thanks so much for joining me on this explainer. Keep wondering, keep learning, and I'll catch you on the next one.